So today we're going to look at computing Legendre polynomials of nth order using recurrence relations. So I'll go through a review of what we've done in the first semester, and then go on to why we use Legendre polynomials. Look at the explicit forms of Legendre polynomials, how they look, and a couple of notations and seed values. Look at the Bonnet's recursion formula, and a couple of problems, and how to verify or know if the solution that you got to those problems are correct. Okay, so first, what we looked at in the first semester was we found the solutions of the Legendre differential equation. So 1 minus x squared y double prime minus 2x y prime plus n into n plus 1 into y is equal to 0. That's your Legendre differential equation. So we did this using a series solution, or the Frobenius method. Now, the series solution was assumed to be like this. So what we did was we found out the coefficients or the values of Cm, and then we used those values and found out what the polynomials or the solutions of the differential equation were. Okay, so now we go on to looking at generating functions of Legendre polynomials. We also did this. Now, using these generating functions, the generating function can also be written as this way: summation of n is equal to 1 to infinity Pn of x t power n. So what we did was we differentiated these generating functions and found out the values of, you found out the recursion relations. We'll come to that later. So now what we did was we expanded this generating function, and we, equated the powers, we looked at the coefficients of particular coefficients of t and found out the polynomials that we have. So now we'll go on to finding out the recurrence relations. That's what we did the last semester. Now what we're going to do here is we're going to use these recurrence relations and find out what values of the Legendre polynomials you get for a particular value of x. So here what you did last semester was collecting the particular coefficients of t power n, and using this we were able to express one Legendre polynomial in terms of the lower two. Okay, so these are primary recurrence relations. We did this last semester, and this is the one we're going to be using most here, because this one is not expressed in terms of the derivatives of the Legendre polynomials. If you look at the other two recurrence relations, or the other secondary or tertiary recurrence relations, all these are expressed in terms of the derivatives of the Legendre polynomials. And these are not of particular use to us because we're looking at the values of the Legendre polynomials of order n. So now if we look at all the other recurrence relations have derivatives of the Legendre polynomials involved in it. Now the other things that we did last semester was finding the orthogonality relations, looking at the completeness of the Legendre polynomials, and looking at the Rodrigues formula. So now we're going to, look into why these Legendre polynomials are important. So if you look at any system in science or mathematics or engineering, or most of these systems can be described in terms of differential equations. In the differential equation, if you have them in the form of Legendre polynomials, you will be able to express them. You'll be able to express these solutions in terms of Legendre polynomials, get plots of them by varying the value of x, and that's what we came across that a little bit in the first semester. So here you look at, there are different ways to evaluate these Legendre polynomials. We're looking at just one of them. We're just looking at the recursion relations. So the different ways to evaluate these Legendre polynomials are using generating functions. One of the ways to do that is using generating functions, looking at the Rodrigues formula, and then we look at the recursion relation, which we'll be doing now. And this is very rarely known, but you can use the Gram-Schmidt orthogonalization procedure to actually evaluate these Legendre polynomials. Now, why do we use this recursion method to evaluate these Legendre polynomials? So you can use this in a computer. All you have to do is make a recursion function, and you can repeatedly find out the values using the two seed values. We're going to be discussing that. So these are very accurate. You can get almost the same value that you can do using the explicit form, that you can calculate using the explicit form. So these are the different explicit forms of the Legendre polynomials that you can calculate. Even these can be calculated using the recursion relation. So if you know the Bonnet's recursion formula, you can use the Bonnet's recursion formula to calculate these explicit values of the Legendre polynomials. Now, how do these polynomials look? So if you look at the 0th order P0 of x, it's 1. And P1 of x, it's x, so that's why it's linear. If you look at the third one, you know it's quadratic, so that's why you have this kind of linear look. You know, you have a parabola kind of a look. And you, as the orders go higher and higher, you know, the number of curves that you have, it goes higher and lower, and things like that happen. So the next thing that we look at is these are the things that you need to remember. So it's very easy to remember. So n refers to the order of the polynomial. X is the point of evaluation, the value that you need to evaluate the point that you need to evaluate the function at. So now we look at two base cases. If n is equal to 0, then the value of the polynomial is always 1. P0 of x is equal to 1. And if n is equal to 1, then the value of the polynomial is always x. P1 of x is equal to x. So these are the seed values that are required for this recurrence relation. So if you're writing a program for this, what you basically do is you give these two values, and then you keep using this recursion function. You feed the value that you have to itself. So using these two, you can find out the Legendre polynomial for any value, any order. So you can find out the Legendre polynomial of any order using these two seed values. So this is the Bonnet's recursion formula. Okay, so I'm using a different form of the Bonnet's recursion formula. So if you go back to this, okay, so if you go back to this, what you can do is you can substitute n is equal to n minus 1 over here. Just a minute. Okay, so if you substitute n is equal to n minus 1 over here, what you end up getting is 2 into n minus 1 plus 1, you get an x. Pn of x is equal to, this becomes n, right? N minus 1, n. You get a Pn of x, and you get an n minus 1 into Pn minus 2 of x. This is 2. So now what do you get here? You get a 2n minus 1 x. This is Pn minus 1 actually, n minus 1 of x. And you get n Pn of x plus n minus 1 into P of x minus 2. You get n Pn of x is equal to 2n minus 1 of x Pn minus 1 of x minus n minus 1 Pn minus 2 of x. Okay, so that's what you get. You use this different form of the Bonnet's recursion formula. Okay, so you use the different form of this Bonnet's recursion formula that you have, and this is what you get, right? So you use this in order to find the higher orders of the Legendre polynomials. So let's go to a problem now. You need to calculate the value of the third order Legendre polynomial at x is equal to 5. Okay, so you want to find out the third order Legendre polynomial. So you express this in terms of the second order, the first order. Take the second order, express it in terms of the first order and the 0th order, and then you get your value. Okay, so let's just look at this. Okay, so this is the Bonnet's recursion formula. You're given that n is equal to 3 and x is equal to 5. You substitute this here, and then you know, it's just simple mathematics. You have P1 of 5 is equal to 5. Why is that? You end up getting your P1 of x is equal to x. So for any value of x, you end up getting the first order polynomial as x itself. Can anybody compute the value of the second order polynomial and tell me the value using this recurrence relation, and tell me the value of P2 of 5? This one here. this one's value. Using this recursion formula, you do 2p2 of 5 and you compute that. Can anybody do that? Anybody?
Dear students, okay, the answer to Vidhu, she asking about the problem.
What is the value of
NP?
what is the value of P2 of 5? It's pretty simple. All the stuff is there that you need on the slide.
Vidhu, once again we explain that problem, that NPNS, and how you substitute to that n is equal to 3 and s equal to, but yes, it is everything in the slide. Just we explain it, okay? Because students will listen so your explanation, okay?
Okay, so if you have P3 of x, okay, or P3 of 5 here, P3 of 5, how do you get the value of P3 of 5? Okay, so let's just go back 1 second. Okay, so you've been given this to you, you've been given the recurrence relation. Now, what do? You need to find P3 of x, right? So what do? Here you have a 3p3 of x. Okay, I will write that as 5. Okay, I will write that as 5. Okay, is equal to 2 into, what do you have? You have 3 minus 1. P of 3 minus 1 of 5 minus, you got n, which is 3 minus 1. P, you got 3 minus 1, which is 1 of 5, right? So you got, what is this? 3 2s are 6 minus 1, which is a 5, P2 of 5 minus, you got 2 P1 of 5. What is P1 of 5? P1 of 5, any Legendre polynomial of the first order is the function, it's the input value itself. So what do you have? You have 5 to this minus 2 into 5 itself. What is P2 of 5 is what we need to calculate, right? So I will just clear all of this. Okay, so you need to calculate this. You got 5 into 5, P2 of 5 minus 2 into this. Okay, you want to find out what P2 of 5 is, right? So what do? You write P2 can be written in terms of P1 and P0. So you've got the seed values back once you do P2. Okay, I'm proceeding forth. Okay, so you want to calculate P2 of 5. So what you do is P2 of 5, when you calculate it in the same manner, is 37. Okay, so you substitute that and you get your 305. Substitute it back and you get the value of 305. So now you can verify this value using the explicit form of the Legendre polynomial. So this is the explicit form of the Legendre polynomial, and you substitute the value of x into this. So once you substitute the value,
I have one doubt. Hello.
Yes, sir.
That P2 value we have to take. So what to obtain in the earlier? So that value you have to substitute here. P2 5. That is
P2 5 we need to calculate it using the this recursion relation. So if you have P2 of 5 here, 2 P2 of 5 is equal to, you have 2 into 2 minus 1, which is 3. 3 into 5, P1 of x. So this is P1 of x becomes x. That's 5.
Okay.
And the other one becomes 1. The other P of 2 minus 2 is P of 0 of x. So that's going to give you P2 of 2. This is going to give you 1.
Okay.
So I'll just calculate it because I did not do P2 of 5 for you explicitly. So P2 of 5 is equal to 2 into, what do you have here? 2 minus 1, P of 1 of x minus, what do you have here? 2 minus 1, so that's 1. P 0 of x, this is going to be 1. Okay, so you have 2 P2 of x, 2 P2 of 5. This is going to be 2 2s are 4 minus 1, which is 3 P1 of x minus 1 into 1. So what do you have here? You have this value is x itself, so that's actually a 5. So 3 into 5 minus 1 divided by 2 should give you your P2 of 5. I think I missed a 5 here. I missed a 5 here. So into 5 into 5. 5 5 is a 25. 74 divided by 2 should give you a 37.
Okay, so nice. So finally, so we got the value of P25. That is the value is 37.
Yeah.
So this value you have to substitute in the next problem, in the next equation.
This value you have to substitute in the previous equation that you got for 1 second. Okay. So this value that you found, you have to substitute it in the previous relation that you got. You've written 3 in terms of 2 and 1. Now you need to write the order 2 in terms of 1 and 0. So you substitute back the value 2 into the order 3 equation. So after you do that, you end up getting this 25 into 37 minus 10. You end up getting a 305.
You substitute that P2 value, that is the value 37. So finally you got the P1 5 is equal to 5.
P1 of 5 is 5, yeah.
Hello.
So your voice is very feeble. Hello? Okay, so what we need to do is we want to verify whether our answer is right. So what we do is use the explicit form of the Legendre polynomial, if you remember it. And then you can substitute the value of 5 into this and you end up getting the same value, 305. So you can see that this is a very good method to actually calculate the values of the Legendre polynomials. So if you don't remember the explicit form, how do you go about that? So you can use the same recurrence relation. So the only thing that you need to remember is the Bonnet's recursion formula and the two seed values that you have. So you substitute this value n is equal to 1 into this equation that you have. And this Bonnet's relation formula, the earlier one without the n is equal to n minus 2, the earlier one that you have. So you substitute n is equal to 1, you end up getting a 3x p1 of x is equal to 2 of x plus p0 of x. And now you know that p0 of any value of x is 1, p1 of x is x. So you substitute those two values, you end up getting 3x squared is equal to 2p2 of x plus 1. So you want to find out what the second order is, right? So what you can do after this is you can get p2 of x is equal to 3x squared minus 1 divided by 2, which is what you got earlier. Okay, so using this, if you want to find out the third order, you have to find out the second order and then go forth like that. So you'll have to substitute this back again and do it. So this is pretty much it. This is calculating the value of the nth order Legendre polynomial using recursion relations.